First of all, I would like to thank the convener for giving me the opportunity to present my work over here. So today I'm going to share my experience about light interaction with natural photonic architecture. The experiment was done, Professor K.P. Singh, laser experiment, and simulation was done, his MS Master of Science student. So today I'm going to talk about optical functionality of natural photonic structure on the transparent insect wings for biomimetic application. So here is the plan of my talk. First of all, I will little bit introduce you what is photonic architecture, following the motivation. After that, I'll come to the experimental observation of spatial correlation and symmetry in natural photonic architecture. And after that, in order to support the experimental finding, we have done some simulation, theoretical understanding of experimental finding, following the analysis part of this experimental observation, and finally, I'll come to the summary and ongoing work. So here I'm showing this. Nature has developed a gorgeous architecture in the insects, beetles, and my intention to show this transparency just give the flavor. There are many photonic architecture present in the natures. So if you, for example, if you look at very carefully the butterfly wings, or if you go from top to bottom down, then you can see that there is a hierarchical arrangement of the natural architecture from nanometer to micrometer scale. When you shine the light, then the spatial variation of these microstructure interact with the light and shows the various optical effect. And one can see the various color in the butterfly wings due to this effect. So if the arrangement of the microstructure are regular, then they exhibit a band gap in their optical modes, prohibiting propagation of light in that frequency range. Then the system is called the photonic band gap system. Otherwise, if there is no regularity in the system, then various optical effects come into picture, like a scattering, diffraction, or interference, like that. So natural photonic is there are two types of color in nature. First is chemical color, and second is structural color. So I'll be concentrate on a structural color. A structural color means when you shine a light on a photonic architecture, and the arrangement of the architecture at the optical wavelength scale interact with the light and shows the various color using 5 physical phenomena: the thin film interference, multiphase interference, scattering, diffraction, and photonic crystal. So today I'm talking about only the transparent wings. Why we are interested in transparent wings? Because the transparent wings have attracted much attention in recent years, not only because of potential application in modern optical technology, but also as the fundamental test bed to manipulate the light for a desirable state. So this is the dragonfly wings, but the structural arrangement on this wing surface in a random order. And this is the domestic fly. This one can see the various color in the wings at a dark background. It means there is a interference, thin film interference. Because of this thin film interference, one can see the various color. I'm interested in not a perfectly transparent wings, or not a perfectly disordered wings, or perfectly ordered wings. This is a fly which is found in India in a rainy season, in a July and August in India. So this insect actually comes in the rainy season and start roaming around the night around the light. So the insect actually having the wings which is not perfectly transparent, and the microstructure arrangement on the wing surface is not a perfectly ordered. It is a quasi-ordered structure. So I'm interested in this sort of structure, because what's so special about the quasi-ordered structure? Why is so important to the photonic community? The law of light propagation in completely ordered and disordered structure are well understood. But what is the behavior optical wave in intermediate regime? I mean in a quasi-ordered state. So these microstructure could be in the various shape, size, and orientation. So due to the presence of multiple length scale and diversity in their design, such shape, size, and arrangement, this shows a multifunctional behavior like a broadband reflection, anti-reflection, anti-weighting property, antibacterial surface inspired by cascade wings. So the motivation behind my work is this: nature actually developed a remarkable variety of photonic structure in the insect wings. So the cooperation of structural heterogeneity in these natural biophotonic architecture at optical wavelength scale interact with the light in a specific way to produce various optical effects. Hence, understanding symmetry principle in natural structure or arrangement is crucial. The symmetry means over here that the arrangement of the microstructure on the wing surface is not regular. The different portion of the wings having different arrangement of the microstructure. So at a particular portion of the wing surface, I am calling this is symmetry. The different portion of the wings have different symmetry. It means this the various arrangement involved on the wing surface of the microstructure. So I am saying that this was the spatial symmetry on the wing surface. So how to probe this structural arrangement of the wing surface. So one can use SAM-TAM because these techniques, no doubt these techniques are very useful in order to give the local information about the arrangement of the microstructure. But if you want to probe the global, if you want to know the global information about the arrangement of the microstructure of the wing surface, these techniques actually are not useful, because these SAM-TAM or AFM technique gives the local information of the system, not global information. So transmitted diffraction technique is the useful optical method for better understanding of the spatial distribution of micron and submicron structure in the whole transparent insect wing in a single shot. So how the natural photonic complex system are assembled in a local and global length scale from nanometer to micrometer. So I want to probe these things. Is there any long-range order and organizational symmetry in the array of microstructure on the transparent wings? So can we exploit complex diffraction pattern to quantitatively unveiling new feature in the arrangement of microstructure array? So here I am showing the various wing surface, transparent wing surface. This is for wasp, this is for the honeybee, and this is for cascada wings, and this is for some I don't know the insect name, but the common feature of all wings is that there is a microstructure arrangement of all transparent wing surface. So this is the generic feature of a transparent insect wing surface. So the arrangement of these microstructure manipulate the light in according to your requirement. So SAM image of various transparent insect wing surface morphology showing pillar-like structure, or I'm saying that this is a hook sort of structure on the wing surface. So purpose of these microstructure on the wing surface is multifunctional, like signaling, anti-weighting, self-cleaning. So in order to give the answer of my question, we have done some experiment to probe the spatial correlation in the arrangement of the microstructure and symmetry. We have used these three types of laser: green laser, monochromatic, monowavelength green laser, red laser, and the broadband femtosecond laser system. So this is my laser system. We have this is a sample holder in which one can put the wings of this insect. And my wings is not a perfectly transparent, so here is I'm showing this transparency, the 60 to 70% transmittivity of the wing surface. This is the SAM images of any portion of this wing surface. So one can see that there are a microstructure arrangement on the wing surface. So here is the experimental finding of our wings. This is the beam profile of my femtosecond laser system, and this is the green laser system beam profile, and this one is the red laser beam profile. So one can see there is a more pronounced diffraction pattern up to second order. So if you can see the diffraction pattern on the screen, it means there is some regularity in the arrangement of the microstructure on the wing surface. But this regularity is not a proper regular way. The structure arranged is not a proper regular way. Actually, the disorder and order play crucial role in order to build this sort of diffraction pattern on the screen. So this right column is represent the intensity cut along this direction. So in order to probe how to build this diffraction pattern from local to global scale, it's just a simple diffraction pattern formula, but I'm concentrate on these things. Diffraction pattern is just equivalent to the Fourier transform for any aperture. So if you take the SAM images of the wing surface at various length scale, so my A images of the wing, SAM images of the wing surface at 200 micrometer length scale. This is 100 micrometer. This is 10 micron, or this is 1 micron. Or one can see that there is only single microstructure on this image. So when we take the FFT of this image, so one can see that there is a more pronounced diffraction pattern. Or if you go down 100 micro scale, diffraction pattern is still there. But when you again go down to this 10 micron length scale of the SAM images, the diffraction pattern is starting to disappear. But when you take the FFT of a single microstructure, there is no signature of diffraction pattern. It means this diffraction pattern is the collective behavior of the arrangement of the microstructure. It's not coming from a single microstructure. So, how to go back? Okay. So, in order to ensure that this is not coming from the single microstructure, we have done some experiment in order to probe this diffraction pattern. We have focused our laser spot size up to 5 micron. Earlier my laser spot size up or the order of 2 millimeter, but now we tightly focused our laser spot size up to 5 micron, and this microstructure size is of the order of 10 micron. So if you scan the laser spot size on the wing surface, when you are here at A position, then there is this sort of diffraction pattern come into picture on the screen. When my laser spot size near about or on this surface, this means this sort of diffraction pattern come into picture. It means this is ensure that the diffraction pattern we have observed in our experiment is not coming from a single microstructure. It is a collective behavior, or it means the organizational property of the microstructure play a crucial role for build up a diffraction pattern. So, in order to go into more detail about the forming of diffraction pattern, we have a simple qualitative model to provide further insight into the experiment by generating a far-field diffraction pattern from two-dimensional array. What we have done over here, I'm not going into detail all these things. What we have done, we have created a regular array on this using MATLAB programming, and we start putting this small noise, and corresponding we measured the diffraction pattern, and by this simulation we actually want to probe this how much the small noise actually sufficient to produce the diffraction pattern which we have observed experimentally. So what is the optimal disorder actually necessary to produce our experimental finding, which is resemble to our experimental finding. So this is theoretical understanding of our experimental result. We propose a simple qualitative model based on optical diffraction by array of non-overlapping microstructure with minimum disorder, which support our experimental observation. So A represent when there is no disorder. So one can see that the FFT of this structure, these structure are not very close to our experimental finding. And the second picture B, we start to insert some noise in shape or size, but not orientation of the microstructure. So we can see that we are very close to our experimental finding. But when we put along with the shape, size, noise, we put the orientation of the various portion of the microstructure arrangement, then this FFT gives the same result as we observed in experimental finding. So this gives actually the role of disorder, role play of the disorder in order to build up the diffraction pattern. So these are the theory. We have used many noise. We have put a noise in a shape, size, and orientation. We have found the various diffraction pattern. But this one is last one is very close to our experimental finding. It means there is a shape, size, and organizational disorder in the structural arrangement play a crucial role. So here I am showing the very interesting feature of the arrangement of the microstructure on the wing surface. When we scan the laser spot size on the wing surface, what we have observed that our diffraction pattern start rotating from this direction to this direction. It means the various symmetry involved in the arrangement of the microstructure on the wing surface. So we have done this experiment by using simple red laser, green laser, and in order to support our experimental finding, we have take the same images at various portion of the wing surface and take the FFT, which gives the same signature as we have observed in an experiment finding. It means the signature of a spatial correlation and symmetry. These diffraction pattern actually gives the various symmetry involved in the organization on the wing surface. So one more interesting things we have observed that one can use our technique to probe the genetic mutation on the wing surface. Suppose this one is without mutation, and we shine a laser on this wing surface, then we can say that there is a diffraction pattern. Okay. So we have another measured some microscopic modulation of mechanical property of transparent insect wings. So we have seen that there is a background and the structure having at least 2 order of magnitude difference of adhesion and fraction properties. So we have probed the natural complex structure in transparent insect wing by simple non-invasive real-time optical diffraction technique using monochromatic and femtosecond laser. Our experimental observation of a stable and reproducible usual correlative diffraction pattern in transmission, unveiling the signature of a spatial correlation in structural symmetry at various length scale for a large variety of insect wings. So this is the generic feature. So the rotation of diffraction pattern we are obtained when the laser beam scanned the various region of the wing surface. This rotation of the pattern gives the signature of a spatial symmetry in the structural arrangement. And this significant rotation ability of the diffraction pattern could be advantageous for mimicking the structure by lead to a novel optical devices. So we have observed strong spatial modulation of nanoscale fraction and adhesion of the transparent insect wings. So this is another interesting feature when we have observed when the distance between the screen and the wing sample is very large, then we have observed this one is when the screen is very close to the insect wings. When the distance between the screen is insect wings and the screen is very large, then when we can see that the diffraction pattern of the zeroth order gives some strange sort of behavior. When we use the green laser, we have seen the zeroth order in such a way that when we use red laser, this one is the red laser zeroth order output. But when we use the femtosecond pulse laser system, we have observed the fractal sort of diffraction pattern in the zeroth order. So the analysis is still being going on. So here I am going to address this question. We have seen that there is a same arrangement of the lens array in the insect eye, and there is same arrangement in the wing surface of the microstructure. So is there any functional correlation between these two? So thank you very much for your attention.
Thank you very much. Very interesting.